Hi, she's Callie.
And that's Steven.
And this is Lab 9 Diffraction with Michaela May.
For this part of the experiment, we are using a camera to view the observation plane on a CCD camera. And by moving the camera along the axis, we view the diffraction patterns from an image of the aperture through the Fresnel region and then into the Fraunhofer plane. We define Z0, which is the distance from the aperture plane to the observation plane. And to do this, we use the different size slit, diffraction slit patterns, and then calculated for Z0 to get it in centimeters.
As we move the camera closer to the source, we get into the Fresnel region where you can see this diffraction pattern kind of blurs together and widens out. But as we go to Fraunhofer, we see the lines decreasing in width till we have a nice crisp pattern with clear peaks all in a line. See the Fraunhofer diffraction pattern for the 160 micron slit. You can see lots of little peaks all in a line here, brightest at the center and getting dimmer as we head out. Using double slits, we can still see that the frequency of the primary diffraction patterns increases as we increase the slit distance. But now, as we vary the distance between the two slits, we also see the secondary diffraction patterns show up, and they also increase in frequency as the distance between the slits increases. Upper pattern for the square aperture, and as we move into the Fresnel region, you can see the edges converge into a plaid or squared pattern. For the circular aperture, you can see these distinct circles and rings, and as we move into the Fresnel region, you see the bright spot in the center gets much larger, and they're not as distinct between each other. The triangular aperture, and you can see as we move into the Fresnel region how these triangles on the edge begin to converge towards the middle and change the shape of the pattern. This is the image of the Fraunhofer diffraction pattern that we saved and then plugged into MATLAB. See on our graph that the maxima are represented by black lines and the minima are represented by the red lines. The minima are not directly in the middle of two maxima, and this is because the intensity is falling off, and although the area is the same, the radial distance may not be the same. So they should not be equally spaced.
We calculated I over I naught at the first maxima and the second maxima, and as you can see, both of our answers were much larger than what we wanted. The error in this could be due to either our image not being centered or it being overly saturated.
If you enjoyed this video, make sure to smash that like button and please subscribe to get notifications on future posts. And also, please comment below what your favorite diffraction pattern was so we can have a rigorous debate.